Okay, so question 4 is about this truss down here. And one thing you may note right away is that this truss has a lot of elements. But it is okay, don't be intimidated by that. You can use SAP 2000 if you'd like from here. But what this problem is really trying to stress is, can you make observations, like can you look at this more broadly? Can you take a step back and look at this and identify what the largest tension and compression members are? Note that you don't need to actually find the force in every single member. You just need to find the largest tension and compression force. So if you can take a good guess, or if you can take a reasonable guess even, and just estimate. So for example, take a couple cuts, see how those cuts behave, and try and figure out which load is largest from there, then you will be in good shape. I'm going to look at part A first, but for this problem, keep in mind that this problem is very symmetric, at least for part A, right? You have a symmetric frame. You have symmetric loads. You have some zero force members in here, and I won't really point them out to you, but it'll be good practice for you to, if you can't figure out which ones are zero force members, then go ahead and start solving for member forces, but if you can, then it'll simplify your work a little bit. What I want to do is just look at, if I look at, and actually it'll be, yeah, if I look at this force, because this frame is so symmetric, this force will be the same in this member as, or this member will have the same force as this member. These two members will have the same force. And similarly, for example, these two will have the same forces as well. So you've already cut your work down in half. You don't have to do all of this. You can just like a 1/2, copy everything over to the other half, and you'll be okay. The other thing to keep in mind is that we are looking basically at an arch, right? We're looking at some kind of arch system. If I were to draw an arch out, let's look at this for example. I put a load down here. An arch has only compression going all the way through it, right? So this whole thing is compression. I have some compression force that's developing across the entire arch. If I put an extra load in here, I develop more compression forces, so I have more compression forces in here. I still get some in here, but the point is that I start picking up compression forces as I go further and further down, and I have more and more loads. At the very top, I have the least amount of loads. This is true for any arch. In the top, I have the least amount of loads, but it's the most important. So I don't know if you guys have, we don't have a course in here that studies things like arches and catenaries and other such geometric shapes, but in any arch, you have something called a keystone. This keystone takes the least amount of force, but it is the single thing that provides the arch its stability. So this is, even though it doesn't actually take that much load, you can't have an arch without this element at the top. So what you should find is that you get larger and larger compression forces as you go further along your arch. For tension, it's a different story. If this were like a cable where it was sagging below instead of being perfectly horizontal, and if you had none of these diagonal members at all, then yes, you would have a tension. Your tension would behave similarly to your compression. But due to the way that your thing is laid out, you will find that your tension is not necessarily largest at the ends. And that is just because your diagonals take away some of your tensile force. So look at this problem carefully. I would just make, I would start off by just making cuts. So I would make one cut here. Let's call this 1, 1. I would analyze the forces in here. I would make a second cut, 2, 2. Analyze the forces in here. And then I would make a third cut in here. 3, 3, and I would see what the relationship is between 1, 2, and 3. You should find that 3 is like some sort of average between 1 and 2. And that'll be good practice for you guys so you can just get a better feel for what these forces look like. For part B is interesting. For part B, we're going to remove this middle load. We're going to set this equal to 0. And you're going to flip the directions of the end points. So for example, this will become point 2 like this, point 2 like this, and this will just go away. So one thing to keep in mind here is that even though your loads have changed direction, you still have some, sorry, this is also going upwards, you still have some sense of symmetry. So if I were to look at this section, for example, cut 2, and I were to do a similar cut on the other side, I'll call this 2A. And let me draw that down here. What do I actually see? This will be very basic, but on the left-hand side, I have something that looks like this, P, and I have something on the right-hand side that looks like this. So my vertical reactions, if I'm just looking at these two, members, and I calculate this, sorry, not the reactions, if I look at the diagonal forces, I should see that these two are related to each other in some way. These two, so if I call this F1 and F2, F1 and F2 are related. It's not something that you might expect, but you will see that they will be very similar to each other. And I'm not going to spoil it. I'll let you guys figure this out on your own. But it'll be very interesting to see if you how you shouldn't have to do that much work for part B. It should be very similar to part A, in a sense. One thing to keep in mind, one last point, for part A, your diagonal forces, your internal forces, the forces inside your members will be mostly 0. So you only really have forces along the outside. You'll have forces in the outside arch and in the bottom chord. In part B, that is no longer true. You still have compression forces and tensile forces, but they will be, your diagonals will no longer be close to 0. So for example, if this element here, this what I'm about to say isn't actual values, or just for emphasis. This might have a force of, I don't know, 10 kilonewtons or something. Your diagonal might have a force of 0.5 kilonewtons in part A, but in part B it might have a force of 7.5 or something. So the arch and the diagonal forces would be much closer in magnitude in part B than they are in part A. That's just something to keep in mind as you're working on this problem. Let us know if you have any other questions on any of these problems. I will say that this homework it shouldn't take you too long, but I don't think I think it's a little bit easier than it is in homework 1, just because you were only really looking at trusses as opposed to looking at all of the strengths of materials across the entire semester. So this one should be a little bit more straightforward, but if you have any difficulties with this, please stop by and see one of us, because you will definitely have a truss problem on your midterm, and you'll definitely have at least one truss problem on your midterm, and you will probably have some problem about identifying determinacy and stability in a truss. So if you have any questions on anything that we've done, please stop by and see one of us.